Hey friends, it's Ben again, and this is a video about the root test. So the root test is yet another method that you can determine whether or not a series converges or diverges based on the terms rather than having to actually somehow find out the sequence of partial sums. So this is a test that's really designed to catch things that are sort of like geometric series, but not exactly like them, okay? So it will obviously work well on something that has something like 1/2 to the n or 4/3 to the n or something like that. Those it's going to catch every time. But it'll also get things like, say, n divided by 2 to the n. It just works super well for anything that looks kind of like a geometric series. However, it doesn't work on something with factorials. It's just not set up to do that. So if you see something with a factorial in it or something that feels like a factorial, go to the ratio test. But if you see something that looks like mostly geometric kind of things, the root test is pretty nice, okay? So let's take a look here at our basic information about the root test. So the setup is that we've got summation n equals 1 to infinity of sum a sub n. Now that a sub n could have -1 to the n appearing in it. If it does, notice that right here, we take an absolute value before we start taking the root, and that gets rid of the -1 to the n stuff, okay? So you're going to take the nth root of that absolute value, and whatever limit you get out of that is going to determine whether this series converges or diverges. If the limit that you get is less than 1, then it tells you that the series converges, because basically that's saying that it somehow acts like a geometric series with the ratio, the R value, being less than 1. So that gets you absolute convergence. And if the L is more than 1, then that tells you that it's behaving kind of like a geometric series where the ratio is more than 1. So that would tell you that the series diverges. However, if you get 1, this is not a helpful test. Sometimes you're trying to use the root test and it turns out you just can't use it. Additionally, if you're taking the limit and you can't take the limit, then this wasn't the right test for you. So that's what happens every time you try to take the nth root of n factorial. It's not a well decided thing. All right, so if p of n is a polynomial, all right, so n squared, 15 n to the third plus 9 n plus 6, any polynomial, and you take the nth root of it as n goes to infinity, you're going to get a limit. You're going to get a limit out of it that's 1, always, right? So anytime you get a polynomial, the nth root will go to 1. So consequently, when you've got one of those that has something like n divided by 2 to the n, when you take the limit as n goes to infinity of the nth root of the n, boom, it's 1, all right? And then there's just this note here that the nth root of n factorial, I don't know what it is. I suspect that it goes to infinity, but I don't know. I actually thought, oh, I'll be super smart and I will just write a Python program and see what it gets. But at around n equals 160, it tells me, nope, sorry, can't evaluate that. So it's just that n factorial is so stinking large. So All right, then let's take a look at a root test example here, okay? So this one has -3 to the n power, so the minus makes it alternating, but you've got a 3 to the n at the top and an n to the n at the bottom. So that n to the n, I've sometimes referred to that as a tetration, and that is probably, when you see that, it has a larger growth rate even than factorials do. And factorials have a larger growth rate than regular exponentials do. So when we take the limit that we have to look at here, we first of all take the absolute value. That gets rid of the minus part. So now you just have 3 to the n divided by n to the n. Since you've got the nth power and the nth root, those will cancel out. And now we just have to take the limit as n goes to infinity of 3 over n, which, as you know, is 0, okay? But keep in mind, this was not the nth term test. You know, getting 0 is not a bad thing here. Once we know that we got 0, that limit of 0 is definitely less than 1. So bam, as soon as we know that limit is less than 1, we know that the series that we're dealing with converges absolutely, okay? In this case, it was an alternating series because of that minus, and so we say converges absolutely by the root test. All right, so yeah, that gets us an example of this sort of thing there. Keep in mind, if it's not alternating, you don't have to say absolutely, but if you say it, I'm not going to slap your hand or anything, okay? All right, then let's take a look at another example here. And so this one, the term that you have has 1 minus 1 over n to the n, okay? So that, looking at it may seem kind of familiar. And the problem is that you're going to look at that and probably say to yourself, oh, 1 minus 1 over n, that's less than 1. So this is a geometric series. And it's totally not, okay? So if we try using the root test on this, since we've got an nth root and an nth power, then we know that those two are going to cancel each other out. And we have to take the limit as n goes to infinity of this 1 minus 1 over n, which will turn out to be 1. And that says that the root test was not helpful, okay? But we can still resolve this. We can go in and take the limit as n goes to infinity of the terms. And in a previous example, we worked that out using L'Hopital's rule. And we found out that it was going to be e to the minus 1, which is a little more than 1/3, okay? So that says that this summation n equals 1 to infinity of this 1 minus 1 over n to the n diverges, but it doesn't diverge by the root test, it diverges by the nth term test. Or if you want to call it the Leibniz test, I'm not going to get mad at you, but I always say nth term test, all right? So, all right, let's take a look at another one here. And this one, what I've got is 1.1 to the nth power, okay? So it was, all I really needed here was something that was more than 1. Didn't really matter exactly what it was, okay? So going in here with the root test, you're going to take the nth root of that, and the absolute value you can just drop because there's no negative terms to it. And now on the top part, the nth root and the nth power are going to cancel out. so that your top turns into this 1.1. But on the bottom, you'll have the nth root of a polynomial, which we previously commented is always going to turn into 1 in the limit. It wouldn't be 1 until you took the limit, but in the limit, it'll turn out to be 1. So that means we got 1.1 divided by 1, which is just 1. Maybe I should have had some 2's there or something, but it's a limit that's more than 1. And so the root test tells us that this thing has to diverge, right? So let's look at just one more here before we go. And this is kind of your cautionary example, right? So if you look at the summation of n factorial divided by n to the n, just intuitively, n to the n grows faster than n factorial does, okay? So we kind of expect this one to converge, but we've got to show it. So if we try to tackle it using the root test, the problem we run into is that right here, you have the nth root of n factorial. I don't know what the answer to that is. I went to Google and tried to see if anybody has this worked out in a way that would be easy to read. I didn't find anything about it. So as I say, I suspect it goes to infinity, but when I tried to just graph it or something with Python for fairly small values of n, it started to say that it just couldn't evaluate the n factorial. So we just have to accept that we can't evaluate that. So that means that the root test is not useful in this. The ratio test, however, is, okay? I believe this was an example we worked out in the ratio test video, but anyway. Then if we look at summation 1 over n, that is a harmonic series and we know it diverges. But when we take the root test on it, we see that we end up getting something with a 1. And a 1 is not decisive. It could be something that converges or it could be something that diverges when you get a 1. Here's an example of something that diverges for it. But if you take the summation 1 over n squared, you also get a 1 out of that limit. And that is a series that converges, not diverges. So you can get examples that diverge and examples that converge, and both give you a limit of 1. So fairly frequently, you run into this problem that you have series that you can get other ways, but the root test doesn't help you with. Same thing with the ratio test. There's some series that it's just not designed for. In general, I have always found the ratio test to be more useful than the root test. Almost everything I can do with the root test, I can do with the ratio test. To which you should be cautious and dubious, and you should say, hey, he said almost, and he's a mathematician. Yes. I used to make the claim that you could always use the ratio test anytime that you could use the root test. And then I took a class where the professor presented an example where the root test worked and the ratio test didn't. I was like, oh, so there are examples, but they're not examples that you'll see in a calculus textbook. So it was a graduate level class, and it was a pathological example. Yeah. Anyway, though, so the root test is a good thing to know, I guess. And sometimes it will work out super easy, but there's some examples that you just can't make it work for. All right. Okay. So I think that's it, and I'll talk to you next time.